Welcome everyone to day 2 of our workshop. We're pleased to have Michael Bobker from New York presenting this morning. Michael is the founding director of the CIUS Building Performance Lab and the associate director of the CUNY Institute for Urban Systems. I first met Michael probably almost 20 years ago at a NSF PI conference. He was doing some work with Bronx Community College at the time. About 15 years ago, Michael and I both worked on a Department of Energy project looking at retuning. And retuning was a concept that Srinivas from Pacific Northwest National Lab developed to do data modeling and do low cost or no cost improvements to building system optimization.
Excuse me, Peter.
Yeah, go ahead.
I'm going to have to log out, Robert, that freezing thingy, and I'm going to crash. So please continue, and I'll be back in like 3 minutes after I reboot.
I'll write an IT guy figured out.
So Robert was on the East Coast, we were on the West Coast trying to implement this retuning project. The issue is that the BAS system is producing tons of data. But if no one's looking at the data, no one's analyzing the data to turn data into actionable information or knowledge, as we used to say, then it's just inert. Michael has continued this work and has a new project with Department of Energy, basically working with building technicians, taking the data from their own buildings and converting it into information that can be used to optimize their buildings, and teaching them how to interpret data and turn that data into actionable information. So we're very pleased to have him. It kind of aligns with a project that Bob has been working on with Train, and we'll hear more about that later in this workshop. But I'm very curious to find out how this project is going with Michael. It's a pilot project. It is using a type of software to do data management, and that software may be available to us, I'm not sure. He may still be recruiting for buildings and the technicians that operate those buildings, who are his target audience. So hopefully this is all making sense. Anyway, so it's something that we've been talking a little bit about just in the last day or so, and using campuses as lab. How do we get buildings for our students to work with? And this is one methodology for doing it. And he's, of course, working with incumbent workers. Most of our students are entrants into the field. But this strategy of using existing building data is a challenge for us, and yet it's this solution might be an interesting possible solution that we can look at.
Okay. So I know we're all here to talk about building automation systems as the topic, and I'm assuming that you are all quite expert at it, at building automation systems in many ways, more so than I. I'm really a building systems engineer, not a BAS engineer, and I could not install a BAS. I probably could not troubleshoot a BAS, but I do know how to troubleshoot building systems, especially HVAC, and that's what we're going to be talking about today. So we know that BAS has become a fact of life tool in the life of operators. It's just something that um, most use if they're in a facility of any significant size. In New York City, we still do have a lot of residual pneumatic systems that don't have central control, but less and less, and I'm imagining most of you are on campuses that, in buildings, small campuses that probably have BASs, but we'll have time to talk about that. I'd love to talk about that with you as we go along. So we know that BAS, it brings great visibility to our operation of building systems. We can see things that would take us enormous amounts of time to see, if we had to walk around to see them, if we could even see them walking around. But along with the visibility come hazards. One of the hazards is the failure to walk around. We can see so much on the screen that we don't get up and away from the screen and from our desk and out into the plant and just do what used to be daily rounds. Our senses on the screen, we have a lot of information, but our senses are limited. A lot of things we used to pick up, noises, odors, as well as visual cues. We just don't get that about equipment anymore from the BAS. So this is a hazard of not getting out enough. The BAS also can provide certain kinds of deceptive information. So we can have sensors that have failed in whole or in part. We can lose calibration, so we can get faulty information. And we're so tempted to believe that it's correct that it takes us a while sometimes to see those failures. Even worse is what I've described here as command-only views, where we don't have a full feedback loop. The installation was done, well, to put it bluntly, on the cheap, and an actual status of the commanded component was not wired back to the BAS. So what you see is the command, and if you're not aware of that, if you're not sensitive to that, you think that something's been commanded, but it hasn't happened. A belt broke, a drive motor failed, linkage came loose, whatever. So the status of the equipment is not what you are seeing in the command-only view. There are some other things too, difficulties in when we see 0 and 100%. Is 0% 0% fully closed or fully open? Is 100% closed or 100% open? And that sometimes can cause confusion. It's not always systematic across, even within the same plant. It's not always labeled systematically. So there's some deceptive information we have to watch out for. The thing I want to say most about looking at these screens is what I think of as the snapshot effect. We see a moment in time, and that's what we get. We assume that moment in time is indicative of the system operation, at least for some duration of time. But we don't get a fully fleshed out view over time of what's happening, and that's what I mean by the snapshot effect. And that affects our judgment too about whether things are right or wrong. So we know also that one of the biggest problems in operators, and I know, I think most of you are community college instructors. I'm not sure how many of you do continuing education with incumbent working operators, how many of you are teaching students or some mix, matriculated students. I'm going to be talking really about incumbent operators. And we know that, there's a problem with manual overrides. If an operator gets a phone call or doesn't understand why a piece of equipment is doing something, it's going to go into manual override, and whatever the programming is there, It can be offline for a short amount of time or a long amount of time after that manual override. I work with many facilities where the operators, because they don't trust the BAS system, sometimes for good reason, they don't trust it, they don't know how to adjust it, they don't know how to write in it to adjust things, so they prefer to operate manually. We can get away with that now where we have a pretty clear control logic of sensor condition and response. But as our systems become, in the next generation, become more complex with PV systems and electric and thermal storage, grid interactivity and signals about what should be happening on behalf of the grid in a grid interactive building, for example, the controls programming becomes more complex, obvious to the operator, and we can put operators in very difficult situations where they can't necessarily see what's going on, and yet the phone is ringing, or they're looking at conditions and expecting things to be a certain way when maybe they're not. And the question is, how do we get operators to work with building automation systems in a way that allows them to go to this next generation? And I will hold to you that a large part of that is being able to work with data in the building automation system. And that's something we'll talk about today. So the background of how the Building Performance Lab, and you can all hear me, right? But I can see on my screen that I'm frozen again. So let's see.
Yes, sir. We can hear you just fine. And your presentation is cycling through as well.
Okay. So I will talk until I crash. Maybe I won't crash. Who knows? I won't turn my video off or I'll lose the screen. Okay. So we started, Building Performance Lab has its history in the beginnings of retro-commissioning in New York City, New York State. NYSERDA piloted retro-commissioning in 2005. It was then included in part of mandatory energy audit legislation in the city of New York. That went into effect in 2009, but really started to go into effect as early as 2008, when everyone knew it was coming. BPL was founded in 2006 with NYSERDA funding. The specific mission was to train building operators for enhanced building O&M. Enhanced building O&M and basically retro-commissioning and ongoing commissioning. So in pursuit of that mission, early on we adopted the Building Operator Certification Program. Many of you may be familiar with that. We use that to train operators in basic principles of energy efficiency. And we found many operators very skilled at operating their buildings, but energy efficiency had never been part of their agenda. So this curriculum gave us a way to introduce energy efficiency concepts. And with that base, we later came upon building retuning protocol, as Peter described, that was developed out of Pacific Northwest National Labs. And we developed these as our basic training programs, in addition to other programs that we use to support municipal energy programming. So again, our focus is on incumbent building operators. We have some engagement with academic curriculum now. We work at City College. It's a senior engineering program, but we also work with various of the university's community colleges. So we have some exposure to curricular offerings, but primarily we've added students as interns to give them practical experience, to get them into the industry. Talk about that a little later too. So again, the building retuning protocol from PNNL. There's a link here. They have extensive user information. If you want to start teaching building retuning that website will give you a lot of resources to educate yourself and your students. Basically, the technique is a way of using structured trend data. And you've probably been talking about troubleshooting, so you've been talking about how to use trend data to see the run-up of a failure condition or the run-up, the operating history of a problem condition. So you're familiar with using trend data for that kind of diagnosis. And this is just a further extension of that, where we're using trend data to diagnose operating conditions with respect primarily to energy. We can get that data, and of course the data can't be visualized unless we do it graphically. We found that that parachute-in method of not very conducive to education, as it were. And so we took the curriculum, we adapted it into a multi-week, 5-week course, actually 5 classes over that would be offered over 8 to 10 weeks. We added in assignments for students to work on their own building automation systems, to bring trend charts into the class, to look at certain things, so they had work to do in the intervening time, made it more practical. Can I ask, I can't say show of hands because I can't see you, but can you indicate by speaking up how many of you, who works with incumbent operators in a continuing education format at all? Are there
Show of
people in
hands,
the room
give them a count.
who do that?
1, 2, 3, 4, 5, 6. We're at about 6 total here, Michael.
Okay, out of your room of 20?
25.
And Michael, a number of our students also are working in industry while they're in school as well. So they may not specifically be identified as incumbent workers, but they are working in the industry.
Right, so this may work that way for them.
Yeah.
We took that multi-week approach and we further developed it into more of a coaching approach, which you can find at this link, buildingcoach.org, and we'll talk about that a little bit further. It's really our extensible approach to try to be able to do this training at scale with other people. So we can go on to the next slide. So given that we're working with incumbent working operators, what is it in this training that essentially what do we want them to be able to do when they come out of the training? And the answer is pretty simple, although there's complexity underneath it. We want them to be able to see their system operations from data, from a database perspective, and be able to identify when they can be improved, when the system operations can be improved, especially with respect to energy performance. So as we've said, the DDCBAS gives great visibility, but we have to be able to see through all the data. You know, the data itself is overwhelming, so we have to be able to plot it into visualized trend charts. You know, you're all familiar with that. Some of you may still be using screen view snapshots extensively, and of course you can see all across a system or a piece of equipment or an equipment room. You can see what's happening in one moment, and that can be very useful. But the trend chart, of course, is much richer. You know, you can bring multiple pieces of equipment together to see their performance over time, and you can bring multiple variables into alignment, which is difficult to do when you're just looking at the screen. So I want to shift now to just do some problems, some issues to illustrate. The first couple are pretty simple, and then I'm going to ask you to participate and you know, speak up. We'll turn the sound back on. I want you all to speak up And we'll wait for as long as it takes for people to get engaged in this. The first one of these, and you can go on to the next slide, Robert. The first one of these, pretty simple. Scheduling is about the easiest thing you can look to see. You see on the left, the facility that's running pretty flat. Things are varying, but they're always on, compared to, and this happens to be duct static pressure, but it could be any of various parameters, start, stops. And on the right, you see that you have a day-by-day schedule that's followed with a night setback, very deep.
So I'm assuming you can all see that schedule, heard enough of my comments before I froze to see, what we get in a regular schedule here. We like to see this orderly schedule. Although the note on the right about optimized start-stop, which is, a pretty useful energy saver, it's much harder to plot, and it requires additional variables. It requires at least outside air temperature, and usually outside and inside air temperature. So it becomes multivariate, a little harder to plot that. And we see that operators really have really have a problem with optimal start-stop because it doesn't happening at a regular time. And so it becomes one of these things where the operator's uncertainty starts to come into play. If he doesn't fully trust the control algorithm, what it's doing, he doesn't understand it and trust it, then he's going to override it. And we've seen that this is one of those kind of next generation things where there are new variables introduced that the operator doesn't quite get, and it's hard to get a handle that, yeah, there's an algorithm in there and it's doing something that's correct, that is thought out and is correct rather than just a malfunction that needs to be overridden so that I'm sure that my building is warm when people come in, or if it's summer, cool when my people come in, which of course is my prime directive, as it were. And if I'm not certain the machine is helping me with that prime directive, I'm going to override it. And this is, one of the things we face, again, as we get more complicated control algorithms, control sequences that are not quite so intuitive and quite so obvious. We can go on to the next slide. So outside air is another key energy cost variable, and it can be a little bit hard to see. You might have a damper position indication on your DAS. We see it sometimes, and sometimes it's reliable, sometimes it's not. But here, looking at this plot of several different air temperatures, so we have the discharge air temperature. This is an air handling unit, obviously. Discharge air temperature, return air temperature, those are at the top. We see an outdoor air temperature and a mixed air temperature. So if any of you feel really confident about this and know the answer, the outside air damper, open or closed, don't say it right off, okay? Let's see how many people, and Robert, maybe you can, by show of hands, see how many people get this right off. Is the outside air damper open or closed?
Show of hands. How many people think it is open?
Very irresponsible.
Okay. How many think it is closed?
Many aren't sure.
How many people need a little more time?
Still looking at that. Okay. Give us just another minute, Michael. I'll ask the question. Yeah. Sorry, I rushed it.
That's all right. You didn't rush it. I will tell you that one of my best experiences in teaching this technique came in a class, and we teach incumbent engineers can be a gruff lot, especially if you get a lot of senior engineers. And so they're pretty gruff, pretty confident, and we had them in the second class, we had them bring in a damper, an outside air damper graphic, and one of the engineers came up to me in the class and said, you know, I did this exercise, but I don't see what it's worth. I look at my dampers, so well, let me see your graph, let me see your plot. And I looked at it and I said, you know, this damper is stuck close. He said, what are you talking about? I inspect my dampers. Student's been operating. I said, well, you know, come back next week, look during the week, look at your damper, come back next week. And he came back the next week and he said, it was closed. That one, the linkage was broken. It was failed closed. How did you know that? And he became a believer. So this is a very useful one, and it was basically this plot that we were looking at. So any further answers, Robert? Do you want to see if anyone wants to take practices?
All
Or
right,
you want to take a vote?
let's start with a show of hands. How many people think the damper is open? All right, we about doubled our number, around 10 or so. How many people think the damper is closed? Similar number, a little bit lower. How many people aren't sure? Okay, a couple people aren't
Okay.
sure.
Bob, you're,
So does anyone?
I'm abstaining because they're not considering humidity. I got no respect for control studies.
You want more data?
All right, go ahead, Michael.
Someone who believes that the damper is stuck open. Anyone want to take a crack at an explanation? What you're thinking? Why you're thinking the way you're thinking?
Jenny?
Okay, I'm a little nervous, but I feel like since the mixed air temperature is trending so close to the outdoor air temperature, I feel like that was the biggest indicator to me that even though the return air is coming back above 70, when it mixes with the outdoor air, it trends pretty close to that outdoor air temperature, which would indicate it's mixing with a lot of outdoor air.
Absolutely correct. Okay,
my mom
so-
is sweating.
Now,
Coach.
heard that explanation. Everyone in the room, it probably becomes crystal clear that with the mixed air temperature pinned up against the outdoor air temperature, it means that we've got almost all outdoor air coming in. Very little mixing of the, 70, 75 degree return air. So in a normal condition, we see the mixed air temperature somewhere up in the middle between outside air temperature and return air temperature. But in this case, when it pins close, the outside air means the damper is stuck closed. So if the mixed air temperature is pinned up against the return air temperature, what does that mean? Anyone?
Yep, there are mumblings that the outdoor air would be closed.
Exactly right. Okay. So this was hard to interpret when you first glanced at it, and now it's easy. It's an easy indicator of what your damper is doing.
Michael,
Um,
can I
and-
point out two
yeah.
quick things on the trend here? There are two things here that I find particularly interesting. The fact that your mixed air and your outside air are so closely trending together. Obviously, we say damper stuck open, and I 100% agree. This difference in temperature could be real or it could be imagined. It could be a difference in the location of the outside air temperature, or it could be an inaccuracy between the two sensors. And the truth may be that we're pulling in 100% outside air. The other thing that I find from a control standpoint that's really, really scary is this mixed air temperature is dropping below 30 degrees. If your mixed air is dropping below 30 degrees, you're at risk of freezing coils and damaging systems. So that's another thing that, from my perspective, should be shutting this unit down in an emergency state. So that's,
Yeah, you're going to have an alarm on this. So actually, Robert, you jumped my next question. Do we like this or not? So the outside air damper is open, do we like this or not? And you're right, at these temperatures, we are in freeze hazard. Now, if the outdoor temperature were 50 degrees, would we like the outdoor air damper, the outside air damper open?
Lots of thumbs up.
Right, because we're getting into economizing though. So if we're doing any cooling at all, then that's 50 degrees outdoor air is what we want, and then we would like to see it open. So again, these graphs, multiple functions, and Robert, thank you about that regarding the freezing hazard and the need for alarm or even shutdown. Okay, so the graphic can help us see things that we might not be able to see. Quick question. How many of you see mixed air temperatures in air handling units in your control systems? Anyone have enough experience to say mixed air temperatures used to be not a point? But it is a very worthwhile point to add. It's not in the system, it's an interesting point to add. It's got a lot of value. Okay, any questions on this? Comments? Go on to the next slide.
Next slide is up.
Here. Yeah, and are you in slideshow mode, Robert?
Yes, sir.
Okay, great. So here it gets kind of interesting. So here we've got a set of VAV dampers. Each color line is a plot, time series plot for VAV dampers. Take a minute, try and orient yourself. Read the axes labels.
So there are mirrors or monitors on the sides for those of you towards the back. Those are a little bit more convenient. Get up, take a look.
When you're in slideshow mode, if you move your mouse over to the bottom left, there's an icon that looks like a magnifying glass, and you can highlight each of the things individually.
Now, we're really interested in the occupied hours,
Just click on it.
we see,
Yeah.
There you go.
we see erratic things in ductwork when there's no fan flow in it, so we get some permutation. So we're really interested in the occupied hours segment. So what can you see and interpret? What's your diagnosis and prescription based on seeing this? Seeing these three different plots, presumably of the same system under different conditions. Time period, although, yeah, these are just mock-ups. These are mock-ups to show the different conditions. What would you say are the differences?
Are we ready to move to? We're focused in on the first one here for a second. We're about to move to the second. Peter?
There we go.
You tell Peter when you're ready to move to the third one.
Can we just zoom back out so that we can hear the
Sure.
Yeah, it's best if you look at them all at the same time. I'll give you a little hint, the close detail doesn't matter so much.
This is a great slide, Michael. I like it.
Okay, this is one of my favorites. So anyone want to take a guess at diagnosis of each of these cases? Each case has a separate diagnosis, a distinct diagnosis.
Anyone?
Something happens after lunch.
So there is definitely
That's
something
interesting.
going on there.
There is that bump there, yeah.
I'll take a stab at the first one, if I may, Michael. I would say that
Yeah,
judging by how low our damper percentages are during the occupied time, we're running too much static pressure from that air handler. Those dampers should be trending much closer to the top, otherwise we're wasting a lot of
Interesting.
energy.
Hit your space bar.
Hit the space bar.
It's a space bar?
Did you,
Oh,
did
hit
the
that.
label of
Next
the
slide.
upper left,
What's that?
Watch out.
Oh,
yeah, advance the slide and the label should come off.
So, yep, that operation damper positions all under 50%.
Right. So that's exactly right, Robert. You know, your system is running highly throttled. Everyone's got, you know, more than enough temperature. So the VAVs are throttling. And that means you're driving the system with too much static pressure. You can get by with less static pressure.
Jim has a comment?
It could be all perimeter rooms where have outside influence and ADC.
Could be. That's a good point. So Jim's comment, if you didn't hear it, Michael, was that we could be looking at all perimeter rooms in a winter climate, and that they're all throttled back and are looking for heat instead of cooling.
Well, I would assume that the system provides heating in the winter and provides cooling in the summer, and the same logic holds that, you know, basically what this is saying is that the room thermostats are satisfied. There's static pressure, you don't need all that static pressure. So,
Brad?
Too low a supply.
okay, let's go to the second, let's look at the second one, the second one is the lower start. Can you figure what's happening there? Anyone else besides Robert? Even Robertson?
Anyone? Brad?
Either too high a supply air temp or too low of static pressure.
Did that come through, Michael?
Yes, depending on the season, with respect to temperature, yeah, with respect to the season. So basically, this system is running starved. By that I mean that all of the zones are not getting satisfied very well. They may be getting, you know, you can see that if we assume this is in cooling mode, the rooms are all in the 80s. So the rooms are starved, the dampers are way open. We have enough static pressure in the system.
So can I ask a question related to that, Michael? So in
Sure.
a lot of systems that are using a supply pressure reset, kind of following the ASHRAE 36 guidelines, trim and response type activity, I've seen a lot more systems trending exactly like this as the desired point, because they're trying to keep the VAV dampers open to reduce or to minimize flow restrictions and save fan energy. What do you think on that perspective?
So we're gonna get to that. We're gonna get to that in just a minute.
Okay.
Okay.
There's a lot.
So let's look at the last
Centrifugal pump doesn't work all the way like that.
here, upper right. Someone making a comment, please. Someone have something they want to say? Okay, in the upper right, you can remove the bar. And the slide and the bar should come off. Okay, so the upper right, this is a pretty good operation. This is what we would expect to see normally, where the dampers are controlling in a reasonable temperature range, and they're varying. The damper positions are all varying based on what's happening in the actual room. Some may be core, some may be perimeter, some may be south, some may be east, some may be occupied, some may be not occupied. So, and they're all in this 60 to 80% open range. And that's kind of the normal condition where our static pressure is And again, this is a constant static pressure, where our static pressure is doing what we would think. So the independent variable is the static pressure, right? That's what we can adjust. And we can adjust it. How should the static pressure be adjusted to use less energy? This is starting to speak to Robert's point. But if we can reduce the static pressure, we typically will save energy, even if we have a VFD back at the fan, because that fan will now unload to the low static pressure settling. There's kind of a tail chasing effect here that goes on. The fan slows down to the lower static pressure, and the boxes open back up. Boxes open back up, the pressure goes down a little further, and the dampers start to throttle, and so forth. So it's continuous action, but we're working the system at a lower pressure. Questions or comments? Robert, your comment is quite acute on this, and I think it speaks to the next slide. Well, actually, not to the next slide. We'll get to it in the slide after. Let's go to the next slide.
I don't know if I'd give a problem like this. It's a part problem, it's not a system problem. And we're creating a systems problem based on a parts analysis. And there's so many other variables in that system that need to be described so that you can explain an entire system problem, not just on a percent of operation. How many trunks are coming off of that duct system? What else is happening in the scenario? Is it heating? Is it cooling? I need to bring the full picture, full circle, in order to have an accurate and informed way of presenting the systematic problem, not a parts problem, especially when it's just percent open. We don't have other variables available. And I think the more variables you have to present a system problem in regards to a building automation issue that you're trying to educate somebody about is probably the most effective way to start developing that mentality. And I guess that's my constructive criticism of the scenario. And
Okay, although I'm
the
not
choke
sure I
area,
agree that this is
the
a
fan
part
choke says
problem.
it's a
This
dynamic
is
problem.
showing the
Not a
overall
positive
system function in terms of the static pressure, the response of the parts. Yeah, the individual parts are responding, but they're responding to the load in relation to the static pressure.
We haven't identified the load in this
The-
problem, that's what I was saying. The heating, is it cooling?
Sorry?
I said we haven't identified the load in the problem at all. It's just a VAV
Doesn't
position,
matter.
right?
Doesn't matter.
Right, it's purely a
I
parts.
hear you, but I would contend that, whether it's heating or whether it's cooling, the amount of, the damper positions are showing you the relationship of the amount of air that's getting into the room versus the load.
It's not showing the amount of air, it's showing the damper position. Amount of air is CFM. Yeah, and every VAV has a CFM calculation tied to it. So we don't have enough variables to create a good systematic problem for students. That's all I would suggest.
Yeah, well, and I hear that, and, the kind of student is matters here. If you're expecting if you're asking an undergraduate HVAC student to do a full workup of how the system is performing,
Yes.
then you do need all that data. But if we're teaching an operator how to look at his system and determine something about his parameters, then this visual recognition matters. I would not expect him to start calculating to get that necessarily. Unless, if he had a certain problem in a room, yeah, then he has to look at that. But the point is that this is a system-wide effect that you're seeing here. In the two bad cases, it's system-wide. In the individual case, in the good case, it varies based on the individual part and the individual room level, and that's not a problem. Let's try the next one. one to see how it goes. I think your point about analysis and how you use this in class is a good point. I want to come back to that later as well. So this case is heating coil valve. So take a minute and orient, see what you see here. You see that you have a loop pressure, and you have on the left, and you have the heating coil valve percentage open on the right. The yellow line is the differential pressure, the cooling coil signal in red. You thought about what you're seeing?
Anyone? Do a pop.
I'll give you a hint. This is same problem as the previous one.
So the pressure stays steady, the valve stays steady.
So Jenny says
What would you say about
oh, go ahead, Michael, sorry.
What would you say about the valve positions in general?
Connie says they're low.
They're low, right? They're highly throttled. They're responding to some load. You see some peaks where they're responding to load, but in general, they're highly throttled. Anytime we see a highly throttled device, be it a valve or a damper, we think, oh, there might be an opportunity there. Let's go to the next slide, which is just showing bad operation, okay? In other words, the valves are very highly throttled. We're working at an excess of unnecessarily high pressure in the loop. So here's what we would prefer to see. We've lowered the loop differential pressure, which forces the valve to open up. The whole system works at a lower differential pressure. Pumps less hard. As the valve opens up, the VSD may speed up a little bit, but the differential pressure, the lower differential pressure will allow it to the pump to spend even more time working at a lower speed. Any comment? Can you all see that? Robert, give me
Yeah.
my eyes and ears.
Yeah, we can see it. Anybody
these
have
graphs
any comments?
say.
No, we're good.
Okay, any comments? This unlike the previous, the damper one, this is only showing one valve, and it's not showing the whole population of valves. So typically, when we're doing this kind of analysis with a loop differential pressure, we're looking across the whole population of valves, and we're looking to satisfy make sure we satisfy the worst case. Now that worst case may be something that, indicates that we have a balance condition, we have a road zone or something, so we want to pay attention to that. But in general, the principle here is, look to reduce the loop pressure by looking at your operating components, see if they're highly throttled. You can click again, Robert. And that question, I think I just gave away that question. Okay, it's basically the same. And again,
Still on the same side.
we're going to have VFDs, but we're going to have the VFDs working to a lower set point. Yeah, make sense?
A lot of head nodding, some thumbs up.
Yeah, okay, great. I appreciate, it's really interesting. I'm so used to being in the classroom, and now not in the classroom, I can't even see on the screen. So Robert, you're doing great for me. Thank you. So let's look at another one. This is the implication of the last two that we just did. I'm not sure my animation is here right. You know, we all are familiar with resetting based on night or based on outdoor temperatures. Those are pretty easy ones. Night setback, outdoor temperature reset. But you know, we can also, based on what we're doing, we can also reset based on dependent variables. That is based on system variables. So we see that the dampers are, or the valves are moving a certain way. It indicates that we're at peak load, and therefore we use a higher, we can ramp up. When the valves throttle too much, we see that we're at a lower load, we can ramp down. And Robert, I asked you to hold off on your comment about guideline 36 and the trim and control kind of algorithms, trim and response algorithms. This is exactly that, dynamic resets, and that's a very important feature of guideline 36. So do you want to come back over that? You can hit hit the slide, advance again, and you'll see the data operation. My animation is off. So, the data operation, it has a setback. It has a nice setback during an occupied period, but it's suboptimal in terms of not being able to differentiate between peak and off-peak during the course of the day and really get a little bit more out of that DSD. Robert, do you want to lead any discussion on this?
No, I think we're pretty clear on exactly that, and we are going to work with some of these exact type problems here later today. So I think you're doing great. Just keep on rolling, man.
Okay, good. So, we also use this kind of technique just as feedback to operators on their control performance. So at the top, you can see a condenser water plot where the blue is the actual condenser water temperature. The gray is the outdoor, the wet bulb temperature. And you can see two different cases of approach temperature. In one case, the system condenser water was set to a cooler, a lower temperature, getting to a close approach temperature. That, of course, unloads the chiller and improves its efficiency compared to a prior period where the approach temperature, where they maintained what had been a fixed set point. So, we can show this to operators, and they can say, oh, this is what happened here. We did better here. We kept the temperature up over here for this reason in this case, and we were able to do better over here for this reason, and so forth. So they can use it to track their performance, and also, in real time, they can use it to see that they're moving in the right direction, that their controls are working, or in this case, this was manually controlled, so the operators appreciate this. And the bottom one is the hot water temperature reset. Pretty easy to see that we have the outdoor temperature in green at the bottom and the hot water system temperature at the top. So one is flatlined, the other is varying. We can see that the variation is exactly what we would want for hot water reset. So we can tell, do we have a hot water reset working or not? And it's very easy to see and track that over time. If we wanted to use a similar plot for variable speed drives, it wouldn't be outdoor temperature, but we can also see if our variable speed drives are actually working. Many times we find that variable speed drives are there, but they're pretty much in a fixed position. Sometimes ramp down a little bit from 60 hertz, but often in a fixed position for various reasons. Sometimes good, sometimes bad. Okay, next slide. So You know, we've seen the operators response in many classes. We've been teaching this way for about 6 years now. You know, we get a lot of enthusiasm. They see in their own buildings, they can see things, and they start to understand how to use the data this way. So if there is enthusiasm, as they begin to understand how to track their systems this way, what's the problem? You know. So another interesting thing shown by this is that not only for energy efficiency, but where we have a lot of different zones that you want to track, and these are zone temperatures, you can track that your zones are performing well together. If you have a trend chart set up with all your different zones, it's very easy to see it, rather than what we used to see was at the beginning of every shift, the operator would one by one go through each zone to check that his usually return temperature or room temperature was where it should be. You know, 74-degree room return temperature, my zone is good. So in general, as a rule of thumb. And he would scroll through 15 or 20 of those, making sure here he sees them all at once. And he can see if they're performing consistently or if there are variations when it gets together. So what are the problems? If it is a good technique, and I'll leave that up to your discussion, consideration. If it is a good technique, what's the problem with this greater use? So trends are pretty easy to set up. Are you, Robert, I think I advanced, but I didn't necessarily tell you to advance. Are you at barriers?
We are now.
Okay. So what are the barriers? You know, it's pretty easy to set up trends. Multivariate, it's a little more difficult. The graphics are not always so great. Different formats across manufacturers, across generations. Graphics have been improving as computer costs come down, but can still be awkward. Inconsistency in point naming is always a problem, especially if you're working across multiple buildings and trying to monitor what's going on in multiple buildings at the same point. The biggest barrier probably is that the data setup and analysis is just not seen as part of the operator's job. And I don't know how you're approaching that in classes with students who you're training. I would imagine you're not training them to be operators, although some of them might be. But this data work is just not in the skill set for operators and not in the job description. Operators, we find, are very used to looking at system status, but they've never had much experience looking at time series data other than for troubleshooting a failure, which really is the link. We can go to the next slide. So how do we address these barriers with our training? You know, first of all, you have to have management support. They have to establish that this is what they want. They have to see that these techniques can improve efficiencies and realize savings. There's quite a bit of history. PNNL, York Berkeley Lab, have all developed histories for retro-commissioning, ongoing commissioning, building retuning, all of these existing building activities that show savings in the 10 to 15% range pretty commonly, and sometimes up much higher, 20, 25% in a really poorly run building. Yeah. Another solution is to standardize the data acquisition and processing steps. So PNL has guidance on how to set up the trend logs, what points or what kinds of systems. We at BPL have done the same. We have these cookbooks that tell the operators, well, if you want to look at this, here are the points you need, and here's how to set up your trends. Here's what trends you need set up. Here's what you should see in the graphic. Again, requires considerable effort on the part of the operator. Some will do it. Maybe you have an energy manager in a large facility who's more inclined to do it. What we found is that this is a place where students can really get good experience in supporting the data acquisition and processing steps. So students, we use student interns, we pay them under some of our contracts, and they work with building operators to collect their data, format it, and then they attend the classes that the operators are in and get to discuss the data with the operators. And of course, they get field experience in that process too, so it becomes a pretty interesting kind of co-op practical experience for the students. And of course, it supports the operators in getting to where they want to be, which is not messing around with the data, but seeing the charts. And we have also worked to standardize the visualizations themselves. So it's very confusing when you're in a class and people are looking at economizers and they're looking at all different versions of how it can be represented. It's very hard to teach for that. It can be done. But we're right now trying to take the approach of standardizing the visualizations so that we know they're good, but then we have to get the data into them. So to get the data, we're trying to scale BRT. If you could advance, Robert, we're trying to scale the BRT now in an online format. We have some Department of Energy support for this building coach program, which combines both asynchronous modules. On the right, you see the kind of areas where we have asynchronous modules. These modules are, 20 to 30 minute lessons. These are the categories. There are 2 or 3 modules in each of these categories, in some cases 4. So this is probably, 5 hours, 6 hours of study on the part of students. They're pretty fast modules to go through. And then that's combined, followed with our coaching, synchronous coaching classes, which are action-oriented. Students bring we extract the data, and I'll get to that in a second. We extract the data, we graph it, and the students have access to it at that point for use in the class. If you could go to the next slide, and I think I'm running out of time. I'm sorry I didn't go to the data acquisition is one of the unique parts about this program. It's also proves to be one of the more challenging parts about the program. But we have a couple of different methods, either a virtual machine, a plug-in, actual piece of hardware, or a virtual machine, which we find the IT departments prefer, that extracts the data. It's one-way data communication, outbound only, to the cloud, where the data is database. It's named following HASAC and BRIC protocols. It's then put into the different charts with the different measures that we want to train on, so that those measures are some of the ones we've looked at: dynamic reset, economizer, scheduling, so forth. And so we populate those charts, the students see those, and we train on those, on their data. This is a pilot that we're still experimenting with, it's free training right now for campuses that can access VAS data. We want to try and have their operators try this out, try learning and seeing what they can do with it. So if you are interested, please be in touch with me. I have my contact information here and on the next slide as well. I want to close with a last question to you in terms of discussion, and I hope you can participate. So, can this technique be adapted for into classes for matriculated students? I assume it would have to follow basic HVAC classes, because you have to understand the HVAC systems functions before you can work with this. But would it make a good advanced course? And could it be done with simulation or emulation in some of your labs? And I'm really interested in this question. I really don't know. and I'm really interested in your feedback. So, Robert, do we have enough time for a minute or two of discussion a couple of minutes of discussion on this?
We definitely do. Before we start the discussion, we do have one real solid question from the group, though. Can we share this presentation with everyone? Is that okay?
Yes, that's fine. You have it, and I'm happy to do that.
Yeah, we'll convert it to a PDF, and we will add that to the files that we're going to distribute to everybody at the end. Thank you for that, Michael. Now, anybody have any thoughts? Do you think you could incorporate something like this into your program? Do you think you could create scenarios like this in the labs that you have on site? Or, you know, have partners you could work with in your area to accomplish something similar, or with Michael's help doing exactly this? So, Jim?
Yes, I think it's worthwhile, especially if you have, if your school can work with the facility people and get them involved. Also, it's a very good tool to have the students work with them and understanding what's going on with the systems and how to tune them to better efficiency.
That was kind of my
Have
thought.
you found that, go ahead, please.
Oh, I was just gonna say, that was my thought too, but maybe like just limit it to just a couple parameters or something that they could be monitoring, so, you know, kind of isolate it, but have it real-time data.
Useful.
Yeah, very useful.
But yeah, Jim's idea is sort of the
How do you find,
campus's
collaborating
lab.
with your facilities groups on campus? I mean, I've been working at that on our campus for 10 years, and I think finally I've been maybe able to crack the nut a little bit, but
Well, just a quick show of hands. How many folks have a good relationship with your facilities team on campus? I am pleasantly surprised. So, Michael, over half the group raised their hands on that one. In previous years, it was nowhere near that number, so that's fantastic.
they,
Pierre?
Yeah, so I think this is great because we actually have students that are coming into our class that knows how to read data, but doesn't know how to work on it, like what Michael was saying. So if we could collaborate them, like Ben was saying, right, the technicians and the operators, so it will just make them better overall, right? So now we have the technicians that know, and the data shows you kind of if there's a problem going on, right? It might not be like what Ben was saying, but if it's trending too much, like in a bad way, then you're like, okay, well, let's start looking at how we could fix that now, right? It could be a part, right? Equipment, something like that. So, absolutely.
I think it has a great opportunity for teamwork, both within your classes and outside of your classes, because the truth is, every building takes an entire team to run it. You're going to have operators that are there day to day. You're going to have specialists who come in to work on specific systems. So, Michael, you were going to say something?
no, I was going to push a little bit. I'm really glad to hear that you've got that access to some facilities, some campuses that have access to facilities people. I think that's a real, a real great next step for students. I wonder though if this could also be adapted into some kind of simulation format. And I really don't know. I don't have an answer. These are not rhetorical questions. These are real questions. Some of you may have more experience with teaching with simulations in the classroom than I do. And I wonder if this could be, if you could program this the kind of faults that we might want to see, if you could program it into simulators.
I think you definitely could, Michael. And I think it would be a significant quantity of work on the front end, but once you did develop the base, it would be a very transferable system. So I think it would be doable, but it would be tough. It would be some real work on the front end to set it up.
Yeah, because to create
Okay,
a
you have,
student takes
nobody's
time.
seen anything that is friendly to this, that exists. Okay. And then last question in relation to this is, you know, is it worth trying to do in the classroom? Or is it better just to, you know, work on getting students out into the field and work with the employers to try and implement some of this?
We'll let that question sink in for just a few seconds, and we'll do a show of hands on who is on which side of that argument or question. Who thinks that it's worth doing in the classroom? Who thinks it would be better to push students straight out to industry for it? Who's still processing the idea and it needs some thought on your part? So, Michael, about
I
half
raised my hand.
or a little bit more of the group raised their hands that they think it's worth doing in the classroom. Almost half said that they needed a little bit more time to think on it. I think a lot of them are trying to think how they could implement it in their own programs. And one person did raise their hand thinking that pushing towards industry would be a better option.
Could you click the slide again? Click the slide and go to where my contact information shows up again?
Otherwise, no, it's here.
Oh, sorry. No.
So, and I'm thinking on this as we're discussing it too. I'm wondering, you know, Peter said that many of you have students who are working. So, you know, maybe there's a way to have your students come back after they've been in some of your basic classes and they're working to come back for more advanced classes too. So that it becomes, it goes from, well, it becomes a continuous improvement kind of process, I guess.
And
But at any rate,
Michael, I had a question.
Yeah,
Um,
yeah.
Are you still looking for participants at this point, or is your third cohort on board?
We are, we do still have a narrow window. You know, I haven't really gone into the difficulties of the data acquisition stage, but Peter, when we last spoke, I think I felt that data acquisition was going to go faster than it's gone. So we do still have some time frames for campuses to join in if they want.
And so joining in means you've identified an industry partner with a commercial building, for example, where they want to participate, they want their operators to participate, they're willing to allow their data to be downloaded. Am I putting that correctly, Michael?
Yes, but more directly, it could be with your campus facilities group.
Mm-hmm.
Could be either way.
And so if they see an opportunity there, they should just reach out to you and contact you. I also had a question, Michael. The software that is being used to do the data download and graphic presentation, is that available on the market, or that you're using for the project?
Right. That's a good question. That's a very good question. So the data acquisition, we have an integration partner called Intellimation. I should have put that on the slide here, but you can check them. Intellimation, just the way it sounds. And they you know, that is, I guess, their method is proprietary. They use some tools that are, some of which are open source, some of which are not. For the data acquisition, the data processing, the the graphics, the trend chart graphics are done on a platform called Grafana. It's a publicly available tool. It's just a historian, it's a trend chart historian. Yeah, so there is that element. But I should say that Intellimation is quite committed to not holding on to the data. So the data, after the data is put into a database, it belongs to the customer. So you can port that data to another platform if you want, and the beauty of that is that it's normalized at that point. It's normalized in terms of the point naming, in terms of the trend charts that are automated, the trending that's automated. So that's portable. But yeah, that's a
There's
good question,
Grafana,
Peter.
yeah. Thanks, Michael.
Michael, do you have any?
So again,
Go ahead, Michael, sorry.
I was just going to say thank you.
No, thank you. So,
And I had one comment I wanted to make. So, Michael, your undergrad major was social anthropology, I believe. Is that right?
That's correct.
And one thing that I noticed at the very outset of your presentation, you were talking about the way operators think. And they have a certain mindset. And I can really see where that early background plays into your ability to think about human behavior. And buildings are dynamic systems. It really comes through in ASHRAE Guideline 32 as well, that I know you worked on a great deal, high performance buildings. You have to have management supporting the technician in order to do this. And there's a whole social dynamic and that comes into play.
Yeah, absolutely. Thank you for that, Peter. And it's very behavioral, very organizational, and you have to have that management support, but the operators also have to have the ability, the confidence in what they're looking at and the evidence they have, go to management as well, and this helps them in that respect too. We've found that many operators find that this process helps their thought process, their ability to express and eventually to quantify what they're talking about, what they're seeing, in buildings. I find that I've always found that operators are, they're very hands-on, they're very intuitive, they understand in different ways what's going on with the building, but can't always express that in a way that is that they can make clear to others who don't have that same kind of intuition. So it becomes kind of hermetic, and this is a way to open that up and for them to show what's going on in their buildings in a way that less technical people can begin to see, at least begin to see.
all right.
Robert, I want to thank you, especially you were great as my eyes and ears, and I think saved this presentation actually. So thank you.
Well, I'm glad you're willing to stick with us and make it work. We do have just a moment. If you do, does anybody have any questions for Michael? All the crickets on our end, Michael.
Well, I do have one last question, Michael. Are you going to publish your findings at the end of this, or your results?
Yeah, I'm terrible about publishing, but I'd like to.
Okay.
We'll see what we find.
All right.
We'll have to put together a grant
Yeah,
and I'll help you
that's
out
what
with it.
we'll
Okay, like you dollar.
publish. Okay, very good.
Okay. Thank
Everyone,
you.
All right, thanks.
let's thank Michael.
Yeah.
Thank you again, Michael. Have a wonderful day.
Same to you. Have a great rest of the workshop, and I look forward to working with some or all of you again. Peter, thank you for having me here. Appreciate it.
That's Intellimation.